AP Chemistry Chapter 15 lesson video, part 2. And in this video, I'm going to cover 15.3 and 15.4. So again, y'all, I just want to start by saying, yes, we're in equilibrium, and it's okay. You're going to be okay. All right, we're all going to make it through. All right, so let's keep on going. So in the last video, we learned how to calculate K values. Okay, so we did the products over the reactants, and we either put it in brackets for concentration or put P for pressure and sub the substance. Okay, so now let's talk about what do these K values mean? Like what's K equals 200 versus K equals 1 times 10 to the negative 4? What's the difference? Okay, so remember, K is just products over reactants. Okay, so if K is greater than 1, that means the products amount is larger than the reactants. So we say equilibrium lies to the right and products dominate. Okay, so like for example, if this is our reaction, if it's greater than 1, that means the products are more. And so like I said, we say it lies to the right and we have more products than reactants. However, if K is less than 1, that means the amount of reactants is more. And so we say it lies to the left and there are more reactants than products. Remember, the opposing reaction rates, though, are equal. Okay, so not the concentrations. So it's important to understand that when K is greater than 1, there are more products than reactants. And when K is less than 1, there are more reactants than products. But in any case, at equilibrium, the rates of the opposite reactions are the same. Because remember, at equilibrium, something has to be equal, and it's the rates of the opposing processes. So let's look at our first sample exercise together. So it says the following diagrams represent 3 different systems at equilibrium, all in the same size containers. All right, I'm probably going to have to click back here because I can't see the question. Without doing any calculations, rank the 3 systems in order of increasing equilibrium constant Kc. All right, so let's do that part first. So it tells me what reactants and products I have. So here I can see I have 4 reactants and I have 6 products. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 reactants and 1 product. And here I have 2 reactants and 8 products. Okay, so remember y'all, K values are just products over reactants. That's the most basic way to think of it. All right, so it says, what does the question say? Rank in order of increasing K. That means I want the smallest K first. So the smallest K is going to have the most reactants. So 2 would be the smallest K. All right. And so then something that would be larger than that would next, this would be 6 over 4. Whereas this would be 8 over 2. So the I would be next. And then the largest one would be the third one because it would be 8 over 2. Remember, it's just products over reactants, okay? So super easy. All right, so hopefully that wasn't that bad. And that's it. All right. So then let's see what part B says. I might have to click back here again. It says, if the volume of the containers is 1 liter and each sphere represents 0.1 moles, calculate the Kc for each system. Okay, so let's click back again. I don't have a lot of room to write this, so I'll just kind of write them down here. Okay, so here our K is going to be blue over red. I'm just going to put B over R. All right, and they said that each container is 1 liter and each sphere is 0.1 moles. So here I have 1, 2, 3, 4. So I have 0.4 molar of my red and 0.6 molar of my blue. Okay, so then I just plug in and divide. And so I got here 1.5. All right, so I do the same thing for this one. So this one, the Kc would be brown, which I'll just call B, over green, which I'll call G. So my brown is going to be 0.1, since there's just one of them, molar, and my green will be 0.9 molar. And so once I divide, I got 0.11 as my K value. And then the last one, my Kc would be red, which I'll call R, over blue, which I'll call B. So my red is 8.8 molar over my blue, which is 0.2 molar. And so I end up getting 4. Ooh, that's an odd box. Alright, and so remember, K values have no units, alright? So all we did was just our products over our reactants. That's all we were doing. And the reason I could just use 0.2 for this was it told me the whole thing is 1 liter. If it had been a different size container, I would need to divide to get my molarities. Alright, so hopefully so far this isn't that bad. Remember, we're just using the K values that we learned in the previous video. Alright, so y'all try this one. I'll assume you paused it and did it, and let's look at it together. Alright, so it says for this reaction, Kp is 794 at 298 Kelvin. And Kp is 54 at 700 Kelvin. Is the formation of HI favored more at the higher or lower temperature? So remember, y'all, K is just products over reactants. HI is a product. So I want high products. Since that's in the numerator, I want a large K value. If I wanted high reactants, I'd want a small K value. So then I just look. Well, here K is 794. Here K is 54. So where is HI favored? At the 794. So at the lower temperature. So the lower temperature would favor because it has the higher K value. Alright, so like I said, y'all, if you'll just think of K as products over reactants, it helps a lot to kind of simplify it that way. Alright, so I wrote lower temperature because Kp is higher, which means the products are favored. Alright, so this next thing, again, we're just kind of like proving something right here, so if you don't necessarily follow this exactly, it's not a big deal, but we're about to move into one of my favorites, which is Hess's Law. So the equilibrium constant expression for a reaction written in one direction is the reciprocal of the one for the reaction written in the reverse direction. So if I start like this, Kc is going to be NO2 squared over N2O4, and it just happens to equal in reality 0.212, like when you actually plug in the values. Alright, if I flip the reaction, so see how all I did was I just flipped the reaction. If I flip the reaction, now Kc is N2O4 over NO2 squared. So see, all I did was flip this. And then the Kc value is 4.72. Well, if you take 1 and divide it by 0.212, you get 4.72. So in other words, what we just proved is if you flip a reaction, you take the inverse of K. So you do 1 over. So you know how in Hess's Law, if we flip a reaction, we change the sign of delta H? Well, if you flip a reaction for equilibrium, K becomes the inverse. So it's 1 over, or the reciprocal of K. Alright, so we'll look at what I'm talking about in this sample exercise. So the equilibrium constant for the following reaction is 1 times 10 to the negative 30. Using this information, write the equilibrium constant expression and calculate the equilibrium constant for the following reaction. So we got to write the expression first. Alright, so my K value is my products, which is N2 and O2, over my reactants, which is NO, but it's going to be squared. Alright, but then it says calculate the equilibrium constant. So I also have to get the number. Well, y'all, it's 1 times 10 to the negative 30 for this reaction. If I flip this reaction, I'm just going to do 1 over 1 times 10 to the negative 30. Alright, and so then once I do that, of course, I'm just going to get 1 times 10 to the positive 30. Okay, so like I said, for equilibrium expressions or constants, if you flip a reaction, you just do the inverse or the reciprocal of the K value. That's it. Alright. So, y'all try this one. I'll assume you paused it and tried it, and let's look at it together. So it says for the following reaction, Kp is 4.34 times 10 to the negative 3 at 300 degrees Celsius. What is the value of Kp for the reverse reaction? So if I take the reverse reaction, I just do 1 over 4.34 times 10 to the negative 3, and I get a Kp of 230.4. No units. No units. Okay, so remember, if you flip a reaction, you just do 1 over the K. Alright, so super simple. See, equilibrium is not that bad. All right, so now let's talk about the rest of Hess's law. All right, so in Hess's law, when we're dealing with heat and enthalpy, if I flip a reaction, I change the sign of delta H. Well, as we've just learned, for Hess's law in equilibrium, if you flip a reaction, you do 1 over the K value. So the equilibrium constant of a reverse reaction is the inverse of the forward reaction, so it's the 1 over K. All right, now in Hess's law for heat, if I multiply a reaction by 2, I multiply delta H by 2. Well, when it deals with equilibrium, we don't do that. So the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to that power. Okay, so we're not multiplying anymore. If we multiply the reaction, we raise K to that power. Because remember, the coefficients are the powers. So that's why we got to raise it to that power. And then the last step is, of course, for delta H's, we add the delta H's when we're done. Well, for equilibrium constants, for a net reaction made up of 2 or more steps, it's the product. So that means we're going to multiply. So here, let me just kind of recap that. So when we're talking about Hess's law for delta H, if you flip a reaction, you change the sign of delta H. If you multiply a reaction by a number like 2, you multiply delta H by that. Once you're ready to add the reactions, you add the delta H's. All right, well, when we're talking about equilibrium, if you flip a reaction, you do 1 over K. If you multiply a reaction by a number like 2, you do K to that power. And when you're ready to add the reactions, you don't add your delta H's, your K's, you multiply your K's. But that's supposed to be in this. I don't know what that was, but it was supposed to be in this. All right, so that's the difference. So whenever you're doing Hess's law, you have to realize, like, oh, I'm focusing on delta H's or I'm focusing on K's, and use the correct set of rules. All right, so let's look at some of these together. I love doing Hess's law, whether it's delta H or K, personally. All right, so let's look at the first one together. So it says, given the following information, so here's my 2 reactions, determine the K value for this reaction. Okay, so yeah, I do it just like I did normal Hess's law. I pick something to look at. So here I'm going to pick HO. I have 1 as a reactant. I want 2 as a reactant. So what do I do to this reaction? I multiply it by 2. I don't know why I'm writing above it like that. So if I multiply the reaction by 2, instead of multiplying K by 2, I'm going to square it. Okay, so let me go ahead and write my reactions. I'll have 2HF yields 2H plus 2F minus. And so then my new K value is 4.624 times 10 to the negative 7. All right, so then I'll look at my next reaction. So personally, I'm going to pick to look at this one. All right, I have 1 as a reactant. I want 1 as a product, so I need to flip this reaction. But when I flip it, I do 1 over the K. Remember, don't change the sign. 1 over the K. So I'm going to flip this reaction. So I'm going to write my product side first. And then for my K value, I'm just going to do 1 over this number. And so I got 2.63 times 10 to the 5. And then I'm ready to add up. So remember, opposite sides, the same thing will cancel. So the 2H plus will cancel. And that's it. So I write what I have left. So I have 2HF and C2O4 minus 2. And on this side, I have H2C2O4. And I have 2F minus. That's the reaction that I want. So here, instead of adding the K values, I multiply the K values. I want the product. Okay, so once I multiply, I got 0.122. Okay, so the main thing is a lot of times you'll revert back to doing what we did in Hess's law for delta H. And you'll start changing the sign, you'll start adding instead of multiplying, things like that. Okay, so just be careful. Different set of rules for K. All right, so y'all try this one. I'll assume you've done that, and then we will look at it together. All right, so we have these 2 reactions. We're trying to combine them to make this reaction. So again, let's just pick something to look at. So on this first one, personally, I like to look at HI. I mean, it doesn't really matter what you pick. You just wouldn't want to pick H2 because it's in both of them, but I like to look at HI. So I have 2 as a product. I want 6 as a product. So what do I need to do? I need to multiply this reaction by 3. So for K, I'm going to cube it, okay, because I raise it to the power of 3. So let me write my reaction. So I have 3H2 plus 3I2 yields 6HI. And then once I cube that 54, I ended up getting 1.57 times 10 to the 5. All right, for my next reaction, I personally want to look at NH3. Again, it doesn't matter. You could have looked at N2 also. You just wouldn't want to look at that H2 because they both have H2, so it's harder to tell what to do with it. All right, so I have 2 as a product. I want 2 as a reactant, so I need to flip this. Remember, once I flip the reaction, I do 1 over my K. So I'm going to flip this reaction real quick. So I'm going to write my products first. So 2NH3 yields N2 plus 3H2. So my new Kc, 1 over that, ends up being 9.6 times 10 to the 3. So then I add my reactions. Let me go ahead and cancel so I can see my 3H2's cancel. And that's it. So I write what I have left. So I have 3I2 and 2NH3. I have 6HI. And I have an N2. And that's the reaction that I want. And so again, I don't add the K's, I multiply the K's. So once I multiply, oh gosh, I'm sorry, y'all. I was calling this KC the whole time. They gave me KPs this time. So my total KP is 1.51 times 10 to the 9. No units. No units. 10 to the 9. All right. And y'all, it is possible to flip and multiply. Like let's say I needed 6 of these on the other side. I could flip it, which means I'll do 1 over that. But then I might need to multiply it by 3. So then I would do that to the power of 3. Okay, so it's possible to do more than one thing to a reaction. It's also possible to not need to change a reaction. Sometimes you can just leave it the way it is. That's fine too. And then obviously the K value stays the same. All right, so let's keep on going. So now we got to start talking about when can things not be included in the equilibrium expression? Because right now we've been including all the products and all the reactants, but that's not always the case. Okay, so homogeneous equilibrium occurs when all substances are in the same phase. So they may all be aqueous, they may all be gas, like that. Heterogeneous equilibrium occurs when all substances are in different phases. So you might have liquid, you might have solid, gas, aqueous, whatever. When pure solids or liquids are in an equilibrium mixture, they are not included in the equilibrium expression because concentration can't change. So you only include gases and aqueous substances in the K expression. If you have a liquid or a solid, you don't put it in there. Okay, so let's look at what that looks like. So here, for example, K, again, is always just products over reactants. All right, so I put my product, my PB, because it's aqueous. I put my Cl, because it's aqueous, but I'm going to square it because of the 2. But the PbCl2, which would normally go on bottom. All right, this would normally go on bottom, but it's a solid. So a solid's concentration can't change. It's going to be the same concentration whether you have a lot or a little bit. Okay, so notice here I don't have any reactants. I only have products listed in my K value. All right, so like I said, leave out any pure solids and liquids. So if it says solid or liquid down here, you don't want to include that. All right, so let's look at a sample exercise together. So it says, write the equilibrium constant expression Kc for the following reactions. All right, so Kc is, of course, products. So I am going to use this because it's a gas. So I'm going to do my CO. I'm not going to use this because it's a liquid. So we're not going to use H2O. Then I go to my reactants. I'm going to use this because it's a gas. So CO2, I'm going to use this because it's a gas. So here I don't want to include water because it's a liquid. All right, so let's look at our bottom one. So my K is product. So I go here. I don't want to use this because it's a solid. I will use this though because it's a gas. So I'm going to do CO2, but I do have to square it because of the 2 right here. over reactants. Well, this is a solid, so I don't want that. This is a gas, so I am going to use that, but I am going to square it because of the 2. Okay, so like I said, you don't want to use liquids and gases. You don't want to use liquids and solids. Aqueous and gas is fine because those concentrations can change. For gases, it's the partial pressure that's changing. All right, so y'all try this one real quick. I'll assume you've already done that, and we'll look at it together. So it says, write the following equilibrium constant expressions. So for the top one, it says Kc. So hopefully you use brackets like you were supposed to. All right, so Kc is product. So I go over here. I do want this aqueous. So I put my, I was going to write silver for some reason, but it's chromium. So I put my Cr with a positive 3. This is a solid, so I'm not interested in it. Over reactants. Well, this is a solid, so I'm not interested in it. So then I put my silver ion on bottom, but I'm of course going to raise that to 3. So hopefully you got that one right. Okay, remember, just leave out any solids and liquids. For the bottom one, you're supposed to do Kp. So hopefully you did the pressures instead of the brackets. Okay, so Kp down here, I do my products. Well, this is a solid, so I don't want that. This is a gas, so I want that. So remember, I do P sub the substance, like pH2, and then I put it in parentheses, and then I can add my power. So I would do to the power of 4 over my reactants, which this is a solid, so I'm not interested in that, but this is a gas. So I do P and then H2O, and then I put it in parentheses so I can put to the power of 4. All right, so hopefully you got that. A lot of you might have forgotten how to write Kp differently. Okay, because a lot of times we use Kc so much that it's almost like you forget about Kp. Okay, don't forget about Kp. It works the same, but it looks different. All right, so let's look at the next one together. So the next one says, each of the following mixtures was placed in a closed container and allowed to stand. Which is capable of attaining the equilibrium, this reaction right here? Okay, so we have 4 options, and it's saying which of these is able to make our equilibrium. Okay, so it says pure CaCO3. So if you start with solid, can we form products and then eventually reach equilibrium? Yes, we can. Okay, so that one's fine. That's going to happen. All right, part B, it says you have CaO and you have CO2 at a pressure greater than the value for Kp. So if you have too much of this, then yes, we can go back and make some of our reactants. So B is possible. Here it says you have CaCO3 and you've got CO2 at a pressure greater than the value of Kp. Well, if you have too much CO2, it's going to want to go back this way, so none of it's ever going to make the CaO. So if you can't make, like, you've got to have all the parts for equilibrium to be here. So this would not be able to reach equilibrium. And then it says you start with some of both of your solids. Well, if you start with some of both of your solids, this one can form the CO2, and then it eventually can reach equilibrium. So y'all, these are actually the questions, like, even though eventually we're going to get into some more like advanced math with equilibrium problems, these are the type of questions that a lot of you would actually struggle with. Like on the AP exam, it might say which of the following would not reach equilibrium, and a lot of you would have trouble getting to C. Okay, so it's those conceptual questions that you've got to like focus on. All right, so y'all tried this one. I'll assume you've done that, and we'll look at it together. All right, so it says, when added to Fe3O4 in a closed container, which of the following substances, H2, H2O, or O2 gas, will allow equilibrium to be established in the reaction? Okay, so you already have some of this. Check. So it's saying, which of the following gases would you need to establish equilibrium? Well, y'all, if you look at your reaction, it's pretty obvious. We need some of this in order to drive it this way, and then eventually we can reach the equilibrium. So in this case, it would be the H2 gas. That's what we would need. Okay, because if I don't ever have any H2 gas, these can't ever react to make the reactants, which can then react to make the products. Okay, so remember, you're just trying to get it to where it has the ability to go both ways. All right, so hopefully that one wasn't too bad. But like I said, it's the conceptual ones that'll get you sometimes. All right, so that is the end of video 2. So hopefully, again, it's not too difficult yet. We've learned KC and KP now. We know how to write it. We've done Hess's Law at this point. We've learned how to leave out the solids and liquids. And so eventually we're going to get to something called ice charts. And so again, don't let it become overwhelming. You'll see lots of conceptual type questions like what you just saw, as opposed to some of the more advanced math that we'll go into.